Behavioral design patterns help govern how objects interact with one another. They focus on communication, responsibility, and flexibility in code. Let's start with the observer pattern. The observer pattern defines a one-to-many relationship between objects. When one object changes state, all of its dependents are automatically notified. Think of it like this. Something happens, and multiple other things react. A subject maintains a list of listeners, also known as subscribers. These listeners can register when they're created, and deregister when they're no longer needed. When the subject is triggered, it loops through all subscribers and notifies them. This pattern is powerful because it decouples systems. The subject doesn't need to know who is listening or how many listeners there are. However, failing to properly remove subscribers can lead to memory leaks. Next is the strategy pattern. The strategy pattern allows you to define a family of algorithms, encapsulate each one, and make them interchangeable at runtime. In simple terms, it lets you swap behaviors dynamically. This is often done using an interface or abstract base class with multiple concrete implementations. It promotes flexibility and follows the open-close principle, open for extension, but closed for modification. You'll often see this in systems like abilities, weapons, or AI behaviors. Now, the command pattern. The command pattern turns actions into objects. Each command typically has an execute method that runs when invoked. Commands can be stored in collections like queues, allowing them to be executed in order or at a specific time. They can also be undone, redone, or replayed, making them ideal for input handling and history systems. The trade-off is increased memory usage. If too many commands are stored, the state pattern allows an object to change its behavior when its internal state changes. This makes it appear as though the object has changed its class. A common example is a character switching between states like idle, running, or jumping. This pattern is useful anywhere behavior depends on context. Even simple Boolean flags can represent basic states, while more complex systems use finite state machines. The template method pattern defines the structure of an algorithm, but lets subclasses implement specific steps. You create a method that outlines the sequence of steps, while leaving the details to derived classes. This ensures consistency, while still allowing customization. However, the structure is fixed. You can't easily insert new steps without modifying the base class. Double dispatch is a technique where the method that gets executed depends on the runtime types of two interacting objects. It builds on polymorphism, where an object can be treated as its own type or as a parent type. Double dispatch ensures that behavior is chosen based on both participants in an interaction, enabling more dynamic behavior. The visitor pattern is a form of double dispatch. It separates operations from the objects they act on. Instead of modifying objects directly, you create a visitor that defines what should happen for each type of object. This makes it easy to add new functionality without changing existing classes. However, adding new object types requires updating the visitor. The iterator pattern provides a way to access elements in a collection sequentially, without exposing its internal structure. Common examples include loops that iterate over arrays or lists. The chain of responsibility pattern passes a request through a series of handlers. Each handler decides whether it can process the request. If not, it passes the request to the next handler in the chain. This continues until the request is handled or the chain ends. While flexible, it can make debugging more difficult due to the number of steps involved. The mediator pattern centralizes communication between objects. Instead of objects communicating directly, they interact through a mediator. This reduces dependencies and keeps systems loosely coupled. Managers, registries, and event systems often use this pattern. The Memento pattern captures and stores an object's internal state so it can be restored later. This is commonly used for undo and redo functionality, as well as save systems and games. The downside is increased memory usage if many states are stored. The interpreter pattern translates and evaluates expressions or languages. It processes input based on context, converting it into meaningful output. Parsing strings into values is a simple example of this pattern. The retry pattern handles unreliable operations. It attempts an action multiple times until it succeeds or reaches a maximum number of attempts. This is especially useful for network requests or external services. A property change listener is a specialized form of the observer pattern. It listens for changes to a specific property rather than all changes in an object. For example, a UI element might react when a slider's value changes. The event aggregator pattern centralizes event handling. It acts as a hub where systems can publish and subscribe to events. This helps decouple components, but can make debugging more complex if overused. The null object pattern provides a default do-nothing implementation. Instead of checking for null values everywhere, you use an object that safely does nothing. A variation of this is the black hole pattern, which absorbs all interactions without producing output. While convenient, it can hide real issues if used improperly. The specification pattern encapsulates filtering logic. It allows you to define reusable conditions for selecting objects. For example, filtering a list of users based on age or eligibility. The role object pattern allows an object to take on multiple roles dynamically. Each role defines specific behavior and can be swapped at runtime. This is similar to how characters can switch classes or abilities in games. Finally, injection patterns help reduce coupling by providing dependencies directly to objects. Dependency injection ensures that a class receives everything it needs from the outside. Constructor injection provides dependencies at creation time, ensuring the object is fully initialized. Setter injection allows dependencies to be assigned or changed after creation, offering more flexibility. Interface injection enforces a method for setting dependencies, though it can add complexity. Together, these patterns provide powerful tools for building flexible, maintainable, and scalable systems. Understanding when and how to use them is key to writing clean and effective code. If you found this helpful, don't forget to like and subscribe so you won't miss the next one. It really helps to support the content, and let me know if you want more videos like this. Thank you for watching.